or everything was fine, clear? No question? Well, if there are no questions now today, we will be talking about atomic vibrations. In this unit, actually, this is the next, I mean, this is the same unit, but the next chapter of this unit. In this unit, we will be talking about atomic vibrations. So in previous unit, we talked about continuum model, where the material was considered to be a whole continuous distribution of mass. And then after that, we discussed about the nature of bondings in different types of crystals. And four main kind of bondings were discussed: ionic bonding, metallic bonding, covalent bonding, and ionic, covalent, metallic, and van der Waals bonding. And then there was another kind of bonding, which was hydrogen bonding, which mainly is because of ionic interaction or Coulomb interaction. But since it is specific to the hydrogen, so it is discussed as a separate kind of bonding. Now, having discussed the kind of bondings which are possible among atoms in a crystal or in any material in general, now we will be trying to understand what can these bondings, or how these bondings are related to different properties. And one such property is bond distance, of course, which we saw yesterday. Another thing which is related to the bonding is, or the nature of bonding, or we should say characteristics of the atomic bonds, is also something called atomic vibrations. So in oh, some people are trying to join, sorry. Okay, so in this unit we will be talking of what are atomic vibrations, or how we can understand vibrations of the atoms around their mean position. So basically, the physical concept is something like what we have done in our unit on crystal structure, or our first unit, that atoms in a crystal are uh, uh, present or sitting at well-defined positions, right? And then those positions are decided by the, of course, kind of bond formation which is there in the particular solid. An atom would like to rest at the position when there is no net force on the atoms because of any neighboring atoms. So that is sort of, you can call, the equilibrium distance between the atoms is the bond distance, or that is the separation between the atoms where they would like to sit. Now, the atoms can be seen to be similar to that of masses attached to a spring. Why so? I mean, mass can be considered to be, sorry, the bond can be considered to be like a spring. So what happens when we have, suppose, one mass attached to a spring which is fixed at one end to suppose a rigid support? Then what will happen? The mass will actually be resting at some equilibrium position, which is actually related to what is the length of the spring. So mass will be resting at a particular equilibrium position. Now, okay. Now, when we try to distort that mass, or disturb that mass from its equilibrium position, what will happen? It will again try to come back to its equilibrium position, right? And because of that, the mass do actually exhibit some oscillations, simple harmonic oscillations. I'm sure you all are aware of that, right? Now, what is similarity of this system with our atoms in the bonds? So atoms actually, whenever they are present in a solid, so they are actually sitting at some specific separation from each other, which is of course the bond distance. And if you try to pull any two atoms close to each other, I hope you remember that potential energy curve. where there was a minima in that curve. And okay, I can maybe quickly try to show up that. Now, since I have learned this thing from Rahul, so that's the kind of potential energy curve, right, which we had seen, where this is your sorry, energy axis. This is your separation between the atoms. So I mean, there is a minima, right, where the two atoms actually are sitting, and this is the separation between two atoms. Now, when you try to push the atoms close to each other, means when you try to decrease this separation between the atoms, the energy will shoot up, right? Means there will be a strong repulsion. And that's something similar to that of a spring, right? When you try to compress the spring, the mass will be pushed back to its equilibrium position. On the other hand, if you try to pull the atoms apart from each other, so because of that bond formation which has happened between the atoms, the two atoms will try to actually come close to each other, and on equilibrium they will be sitting on a specific separation which is related to the bond distance. Now, since so atoms can't be resting at their equilibrium position. I mean, there is nothing like a rigid bond approximation. There's nothing like rigid bond. I mean, it's not that okay, they will be fixed to, or atom will be fixed to this particular position. So what can happen is that because of many effects, like you can expect atom to gain energy from, say, temperature, because of the thermal vibrations. Even at a very low temperature or even absolute zero, there will be something called quantum oscillations, right? So atoms will keep on vibrating about their mean position. So because of those vibrations, there are certain properties which are related to these vibrations. There are many properties indeed. For example, conductivity, electrical conductivity, thermal conductivity, all these things has something to do with atomic vibrations as well. Um, Specific heat, thermal properties, all those are related to atomic vibrations. So in present unit, actually, we are trying to understand a solid and made up of atoms, and those atoms are vibrating and are bound together by some bond, and that bond acts like a spring. So we will be using Newtonian equations of motion here, and we want to understand these atomic vibrations. I think I need to remove this thing. How? Don't know. Just a minute. Huh? Let me again come back to this. Okay. So this is representing a particular direction in a crystal. So in a crystal, in a practical three-dimensional crystal, what can happen? You pick any direction. Then along that direction, there will be some specific separation between the atomic planes. For example, in simple cubic 100 direction, the planes are separated by a distance a, the lattice constant, right? If you talk about 110 direction, then you can find out d interplanar spacing along 110 direction. I think you have done that. D is equal to I think a over under root of h square plus k square plus l square. That was the kind of expression you had done, right? So now here we are assuming a specific direction along which waves are propagating, or atomic vibrations are being studied. And what this is representing, propagation of longitudinal waves along this specific direction. Now, how these waves can propagate? Now you will ask, okay, that we did propagation of waves in the previous case as well, right? Yes, in previous case or in previous few classes, we discussed propagation of waves in crystals, for example, cubic crystal, but there the situation was different. The situation was different in a sense that there we didn't talk about the detailed nature of a bonding between the atoms. We talked or did the whole analysis in terms of those elastic constants. Now, how are those elastic constants coming from the what you can call interatomic interaction? That's what is the part being discussed here. So now we want to discuss propagation of waves via means of atomic vibrations. And this is the one case where we are assuming longitudinal waves. Means, okay, suppose these are the atomic planes, and this set of planes, suppose, is the reference plane. We are saying US. Initially, suppose it is Sth plane, and U is the displacement for this particular plane, and then this is US plus 1, a plane towards right of this reference plane. So suppose initially it was at this distance. So now you see these dashed lines are actually separated from each other by a constant distance, say A. All these dashed line, this is the reference. So all the dashed lines are separated by a distance A from each other. So this is A, this is also A. So this is atoms when they are not at all distorted, and they are on their specific equilibrium positions. Now, because of atomic vibrations, what may happen that okay, one of the plane is, so suppose this is the direction of propagation of the wave, then the atomic plane is, this particular atomic plane is supposed chosen as a reference. So we say, okay, this plane is reference, so there is no distortion on this, let us say, or on this plane the distortion is US, but it is taken as reference. So what will be the next plane at, this will be having a separate distortion of US plus 1. Similarly, next to this one is US plus 2, US plus 3, and so on. So, and similarly US minus 1. So this is in this case atomic planes are disturbed along same direction as that of K, the propagation of the wave. So that is why this is representing the longitudinal wave. Similarly, you can discuss transverse waves in this manner. If K is the propagation vector, then if this is Sth plane, now atomic planes along this direction are not distorted, or they are separated by distance A only. How they are distorted? They are distorted in a direction transverse to K. Atoms are distorted in a direction transverse to K. So that is a transverse mode. So here you can notice that, okay, same notation we are using. US, suppose, is the separation of Sth separation of atoms in Sth plane, or distortion of the atoms in Sth plane, then S plus 1th plane, S plus 2th plane, and so on. So again, here you would notice those dashed circles are actually representing the atoms on their undistorted positions. And then this is distorted, I mean, because of atomic vibrations. Now, these are two different modes which are possible for atomic vibrations. Now, here what we actually are discussing is trying to discuss the detailed aspect of those atomic vibrations, and then how those atomic vibrations can lead to various kinds of properties. So we will be here using Newtonian equations of motion, and what we will keep in mind is that there is only nearest neighbor interaction. I mean, the atom is interacting to its neighbors only, nearest neighbor, not next nearest neighbor or next to next nearest neighbor. Nearest neighbor is usually written as NN, nearest neighbor, and next to next nearest neighbors are written as triple N, next nearest neighbors, and so on. Okay, so now we assume that the force on the plane S, any plane you can pick, say suppose reference plane S, is caused by the displacement of plane S plus P, is proportional to difference. This is actually, we are using Hooke's law, right? So I mean, the force on this plane because of some S plus Pth plane. So this is general thing, S plus Pth plane, not nearest neighbor thing. S plus Pth plane. There, I mean, this atom may be interacting with this atom, right? In general, so P will be 2 in this case, S plus 3, and so on. So the force caused by that S plus Pth atomic plane will be US plus P minus US. So US is the distortion in this Sth atom, and US plus P is the distortion in S plus Pth plane, or atom in S plus Pth plane, right? So accordingly, what will be the net displacement between the two atoms? This will be US plus P minus US, right? So this force is proportional to displacement, isn't it? That's what is the Hooke's law. So that's what we are using here. For keeping our life simple, we are using nearest neighbor interaction so that P is plus minus 1 only. So that total force will be only because of on a sth plane will be only because of S plus 1 or S minus 1. I mean, if we think of this one, so at the force coming on this atom is either because of this atom, the nearest neighbor to the right hand side, and this atom, the nearest neighbor to the left hand side. Is this clear? Any question up to this point?
Yes, sir.
Right. So, what will be the force given by? So, force on sth atom or force on atoms in sth plane will be C. Suppose sort of spring constant. So, C actually depends upon nature of the bond. This is where the characteristic of the bond is sitting. So, bond, which kind of bond it is, that will be deciding the value of C, the spring constant, right? So C into, so S plus 1th plane, what is the force on Sth atom because of S plus 1th atom or atom in S plus 1th plane? That will be US plus 1 minus US. So that this will be net displacement between these two. So US is the displacement for this plane, US plus 1 is the displacement for this plane. Net displacement is US plus 1 minus US. That is going to give us the net force on this sth atom because of this atom. Similarly, the force coming on this same sth atom because of the atom sitting to this side, S minus 1th plane, will be C into US minus 1 minus US. You should notice that the signs are taken care here. So here we are taking US plus 1 minus US. Uh, so this force is trying to act like this, right? This force is trying to act along this direction, and this force is trying to act along this direction. So these directions are taken care here. Here we have written uh, I mean, direction actually, it's nothing like to which side the force is acting. It will depend upon what is US plus 1 minus US. So, what is the net displacement? That will decide the sign. So, if US plus 1 is smaller than US, in that case, force will be acting, it will be minus, so it will be left side, or in other case, it will be right side. Because atoms actually are not, okay, that this will move to this side only, they are vibrating. That's what we're talking. So vibration means this atom can be to this side as well. This diagram is taking a single snapshot of what is going on. Actually, atoms are vibrating about their mean position. So force is it depends upon in which direction the force will act, right? So it depends upon these values of us minus 1 and us plus 1. But this is a general equation. Okay, is that clear?
Yes, sir.
Okay, so if we so basically what we are using, we are not using any quantum mechanics. We are using we are treating our system classically till now, and assume the trying to understand the atomic vibrations within the Newtonian laws of motion, right? Newtonian laws of motion. So the this constant C, the force constant, which we can call, is actually depending upon bond strength, of course, and also this will be different for longitudinal and transverse case. Why so? Because in longitudinal, the bond is directly stretched. You can see bond is directly stretched. So C will be probably higher in case of longitudinal case, and in case of transverse, this will be lower, because it is like, okay, stretching the spring along its length or stretching the spring perpendicular to its length. So C, will be different for different modes. It is convenient in general here. So now what we will be doing is we are keeping C, and we are not bothering about longitudinal or transverse part. We are trying to derive general formalism. Then accordingly, whatever is the case, we put the value of C and then obtain the final results. Here's any question. It seems somebody is trying to ask question. Is it so? No? Fine. So this equation of motion will become what? We just now substituted force because Fs was force acting on atom in sth plane. So this will be acceleration. M is suppose the mass of the atom in that sth plane. So m into a. This is acceleration del square u upon dt square. So this became the Newtonian equation of motion. And what will be the solution for this kind of situation? Is a sort of atomic uh,
Sir, you are not audible.
vibrating because the system is simple harmonic oscillator kind of system. Atoms are trying to go to their equilibrium position, but then because of their kinetic energy, they may overshoot the equilibrium position, and this keeps on going. So that's a simple harmonic oscillation kind of thing, and this is the best mathematical way to represent those time-dependent harmonic oscillations. So if we use this kind of time dependence, because US suppose, or what is the meaning of saying this is that US actually has two parts. One may be space dependent, one is time dependent. So time dependent part, if is this kind, then what will happen? Only this part will give rise to time dependent derivative. So this equation can be solved uh, directly from this dependence, because even if there is some space dependent component, that can be taken outside the derivative, and that will sit finally in the answer as such. So d square u over dt square will actually give this equation. Now if we substitute this, we will find out that okay, m omega square us is equal to this thing, right? So right hand side is kept as such. So now this equation, if you see, is a finite difference equation. I hope you have studied somewhere, maybe in numerical analysis or numerical methods course, finite difference formulae, right? So this is sort of central difference formulae and is representing second order again derivative. It is formula corresponding to second order derivative. I hope you should be in a position to recall that. If not, I would recommend you to go to book by E. Balaguruswamy, Numerical Methods. There you can find out all these finite difference formulae in detail. Well, so this is representing sort of space derivative. I mean, this side was time derivative. This is now this we obtained. Fine. So this is actually representing second order space derivative, and this kind of equation will have a solution. Now this is also a differential equation now in terms of us, and this differential equation will have this kind of solution, that is us plus minus 1 is equal to u e raised to the power iota s into k a plus e raised to the power plus minus, I mean this is something like this is s plus minus 1 means here you can say e raised to the power iota s plus minus 1 into ka, because if you take these common, you will find out the same thing. But okay, we have written it this way. Why? Because of some mathematical convenience, where k is a wave vector in general, and the value of okay, the value to use for A will depend upon the direction of K. Yeah, fine. What will be the A spacing? I mean, A spacing is interplanar spacing. What is this line saying is that this A will actually depend upon along which direction we are going. The thing which I told you in very beginning of the lecture today, that if you are taking 1, 0, 0 planes, the interplanar spacing will be A. If you are moving along A, 1, 1, 0, then interplanar spacing is going to be different. If you are moving along 1, 1, 1 direction, interplanar spacing will be different. If you are moving along say 2, 1, 3 direction, interplanar spacing will be accordingly different. So we don't have to use the lattice constant, but we have to use interplanar spacing. So that's what this line actually mean. Now, if we look at these two equations and substitute the value of us plus minus 1 in this equation, what we can obtain is equation of this sort. You can try this, right? So if we substitute this us, so 1 is 0, so this part won't be there in that case. So this will be u into e raised to the power iota s ka, that's what is sitting here, minus m omega square. Where is it? Oh yeah, minus m omega square. This is us we put. Then this is equal to c into u. So we now are substitute, c and u is going to be common. U will be outside, so c and u will be common here. C into u, that's what is done here. Into e raised to the power iota. So this is s plus us plus 1. So this will be s plus 1 ka plus e raised to the power iota s minus 1 ka sitting here, minus 2 e raised to the power iota s into ka us. I hope that's clear. Is this clear?
Yes, sir.
Right.
Yes, sir.
What will happen is that e raised to the power iota ska can be taken common. So on both sides, so this term will cancel. This cancels this s sitting here, right? Yeah, e raised to the power iota ska, e raised to the power iota ska, e raised to the power iota ska. So this goes with this, right? And even u goes with u, both sides. So what you will be left with is omega square m. The minus is taken to the right hand side here. So omega square m is equal to c minus c into what we are left here finally with e raised to the power iota ka plus e raised to the power minus iota ka, this term, and minus 2. And if we use this identity, means 2 into cos of theta is equal to e raised to the power iota theta plus e raised to the power minus iota theta. I hope you have done this. This comes from Euler identity, right? E raised to the power iota theta is cos of theta plus iota sine theta, right? So if you put the values, so this will be, this e raised to the power iota theta will be cos of iota ka plus iota, sorry, this will be cos of ka plus iota sine ka. This will be cos ka minus iota sine ka. So iota sine ka will cancel each other. One is positive, other is negative. So finally, what we will be left with 2 into cos of ka. So if we use that, so these first two terms will give us what? So this will be like omega square m, or m is also taken to the right hand side. So this will be 2 into cos of ka. That is a minus is sitting here, right? So that minus is taken common. So a minus is taken common here. So that is why this 2 is also taken common. So this 2c by m, 2c by this m came here, a minus already was taken, so this will become 1, this is sitting here, minus cos of Ka. This 2 came already outside, so this will be left as minus cos of Ka. So this gives, or this dependence of omega on this K, the wave vector, is known as dispersion relation. This is known as dispersion relation. Omega versus K. I hope you have studied it. Dispersion relation is very standard thing. In waves and optics, it is a very standard term. Means how does omega depend upon K is what is given by dispersion relation. So in this context, this is representing the dispersion relation for atomic vibrations in a crystal. Means in case of atomic vibrations, how does the omega depend upon K? Now let us see this thing. This is going to be very interesting. Graphical aspect of this thing. And how this is actually related to what you call Brilliant zone thing now. Now we will try to discuss that Brilliant zone once again. Idea of Brilliant zones. So that's our dependence of omega on K. Now, what will happen at first Brilliant zone boundary? Now, we are talking of a specific direction in a crystal, right? So that can be seen to be like a one-dimensional periodic lattice, isn't it? I mean, atomic planes along that particular direction are or can be seen like one-dimensional lattice, so with the interplanar or interatomic spacing being A. So if interatomic spacing is A, so what will be the Brilliant zone in that case? The boundary of first Brilliant zone will be pi by A plus side and minus pi by A. That is nothing but the Wigner seed cell. I hope you remember now that idea. Let me try to quickly show it here. Let me write it down. Maybe that will make it better. So it is like, okay, this is one point sitting here, other point sitting here in reciprocal space, other point sitting here, and so on. Suppose this is our real space lattice where atoms are separated by a distance A. Oh, sorry. Atoms are separated by a distance A. So what will be the reciprocal space for this case? This will be made up of the reciprocal lattice points, which will be again linear, and the separation of those points is given by 2 pi by A, right? 2 pi divided by, oh, sorry. Oh, writing with mouse cursor is very challenging thing. Anyway, 2 pi by A, correct? So what will be first Brilliant zone? So if we take this to be reference, or Wigner seeds will be what? This is 2 pi by A, this length. So what we do for Wigner seed cell? We bisect this plane, and what will be the separation? And we also take this side, again bisect, that's your Wigner seeds construction. So this will be pi by A because total length is 2 pi by A. So this will be plus pi by A. Similarly, there will be another thing here called minus pi by A. So this is representing the zone boundary. That's what we are trying to say here. So this is your Brilliant zone boundary. Okay, is this clear?
Yes, sir.
Yes, sir. Yes,
Okay,
sir.
so the slope of omega versus K will be, so what will be the slope of omega versus K? This is omega square versus K, right? the slope of omega versus k will be okay. We have an eraser as well, I think. Can you try to find out the slope? Okay, the slope will be d omega upon dk, right? If you take the derivative, so this will be 2 omega d omega by dk on left hand side, right? So right hand side, what it will be? This will be 2c by m will be constant. This first term will be 0. 1 minus, so this will be cos of uh, k a. What will be derivative of this with respect to k? This will be sine of k a into a, I think, because derivative is with respect to k. So what will be sine of ka when k is pi by a? So that will be sine of pi by a into pi. Sorry, a. So this will be sine of pi, which will be 0. So that's what it means. I mean, the slope will be 0. Slope will be 0 for this. And this is something really important. What is that slope related to? D omega upon dk is related to velocity, right? Wave velocity. So wave velocity is 0 when the wave vector is equal to plus minus pi by a. Means at zone boundaries, the velocity, when the wave vector is equal to plus minus pi by a, the velocity of such waves will be 0. So that's again a kind of interesting thing for oh, that is done here. Fine. This is what I was trying to say. So at k is equal to plus minus pi by a, this will be equal to this thing. This already discussed will be 0, because when you put k is equal to pi by a, this will be 0. Now, if you, there is some simplification to this right hand side which he has done here. So if you use 1 minus cos of theta is equal to 2 into sine square theta by 2. So what will that become? This expression actually, omega square, that will become equal to 4c by m. Why? But what we have done? This one, 1 minus cos of ka. So to that we have used this formula. And this formula is giving us this 1 minus, 2 into sine square theta by 2. So this is the same thing done here. Okay, so now if we try to see its another form, so this is omega square, right? That is omega square. So what will be omega? Omega will be 4c by m under the root sine of 1 by 2 ka, mod of sine ka by 2. If we try to plot these dispersion relations between omega versus k in, say, first Brillouin zone, how will that look like? Now, this is shown directly here. You can write down any Fortran program, or this is very simple thing, sine of ka. This is sine of half into ka. So what we are varying is k. K is being varied here, because in reciprocal space, what is k representing? K is representing wave vector. So in reciprocal space, it is also k space, right? So now k is representing wave vector of the wave propagating through the crystal. So now you can see that if the wave vector is very small or close to 0, omega is approaching to 0. When k is 0, omega is approaching 0. And this goes like, okay, mod of sine of ka by 2. So sine function's maximum value is 1. So 1 means, what is this value going up to? 1. So this thing is not this thing is actually 4c by m under the root. This is taken actually to right hand side here, left hand side, sorry. So this is omega by 4c by m under the root. So this, and right hand side can be maximum 1. So that's represented here. But this is representing the dispersion omega versus k for a wave propagating in a crystal. Doesn't matter whether it is longitudinal or transverse. Where will that longitudinal or transverse nature will come into picture? That will come in C. This C will be actually deciding whether we are talking of longitudinal wave or transverse wave. But the qualitative variation will remain the same. And you can see something interesting that at Brillouin zone boundaries, this is called Brillouin zone boundary. This one and, sorry, this one here. I mean, K is equal to plus minus pi by A. So at Brillouin zone boundaries, omega is highest. You can see here highest, and you can find out what will be the highest value of omega. That is proportional to, of course, C and M. So omega is directly proportional to C and directly proportional to M, the highest value of omega. And at zone boundary, the rate of change of omega at zone boundaries, rate of change of omega here with respect to k is 0, and that is representing the phase velocity. So you can find out what will be the velocity d omega upon dk, d omega, if you plot the velocity. So you can try to take d omega upon dk from here. How will velocity look like? So from here you can see the velocity is going to be 0 at this. That probably is going to look like this. Qualitatively, I'm saying. Quantitatively, you need to check. How will that? Oh, rather, I don't think it is going to be that simple, because here there is a change, sudden change. So here the value will be large, I mean largest. So here the d omega upon dk, the velocity will be highest, and here it will be 0. You can plot these graphs for, I mean, this graph is not as per this axis. I am just trying to show you the qualitative thing. You take d omega upon dk, this thing will come as a constant, right? And then take derivative of sine of mod of ka, and that will give you a variation. I mean, you need to check what will be the derivative of this. Okay, I leave it to you. You plot this because it was not given in the book and I didn't plot it exclusively for you. So you do it as a small homework, that how will the velocity look in the reciprocal space or Brillouin zone. Okay. Well, that's all. I mean, that's all for today. In next class, we shall be talking about. So this was the case for the monatomic basis. Means our number of atoms per lattice points were 1. There were only one kind of atoms having mass m. Now, in next class, we will be considering atomic vibrations in lattice having diatomic basis. Suppose we have two kinds of atoms, A type of atom and B type of atom. Then if we have two kinds of atoms, how will these things be affected? So that is what we will be doing. And at the same time, we will also be then in the next classes rather using these dispersion relations to understand thermal properties, how we can actually calculate specific heat, how does that omega versus k important there. So all that kind of stuff will be coming in the next classes. Well, that's all for today. If there is any question, I will be happy to help. Yes, any question? Any
Sir,
question?
sir,
Yeah.
I have plotted velocity with respect
Uh-huh.
to k. Graph is like inverted parabola.
It will be like inverted parabola,
Yes,
as I
sir.
told you.
But
Uh,
it depends on a.
uh.
That means velocity is directly proportional to lattice constant.
Yeah, I
But
mean, velocity is directly proportional to,
lattice constant.
yeah, I mean, periodicity will have role, of course. That is fine. But then accordingly, your Brillouin zone will also change. Na? If A will change, Brillouin
Yes,
zone pi by A will also change, isn't it?
yes, sir. Yes, sir.
Size of the Brillouin zone will also change. That's okay, fine. So that is how the velocity is going to look like. That's perfect. Any other question? Yes. No? If there is no question, you quickly sign your attendance, and then that's all for today. Okay, so attendance done. Well,